Hello, dear student. We continue our course of formal language, automata and codes, and today we have lecture number 21. This and other lecture you can find in my web page here. Here you can find. You can to see lecture number 21 about prefix graph of a code. Also, the Ukraine version of my lecture you can find in my website here. So we start. The prefix graph is used to give an efficient test of whether a set X capital is a code. The graph can also answer some other question on the set X capital by applying standard technique for a graph traversal. This will be detailed in later lectures. Let S capital be a finite set of words over some alphabet A capital. We define a graph G capital sub X capital for X called the prefix graph of X capital as follows. The vertices of G capital X capital are the non-empty prefixes of the word in X capital, and there is an edge from S to T if and only if one of the following two situation occurs. Either ST belongs to X capital or ST is equal to T for some X from X capital. You can see the following figure, yeah? Edges of the first type are called crossing. Those of the second type extending. A crossing edge ST is labeled with the word T, and extending edge ST with S multiply X is equal to T is labeled with X. As usual, the label of a path is a product of the label of its edges. In the case where Sx is equal to T and Xt are in the set X capital, then the bar St is an extending edge labeled with X, and the bar Sx is a crossing edge also labeled with X. A vertex S is intended to represent a prefix that has been constructed in the process of trying to build a double factorization, say ys is equal z for yz from monoid generated by X capital. Crossing edge bar St with St is equal S, which is belong to S capital, gives the factorization X Yx is equal Zt, and the prefix T swapped to other side of the equation. Whereas an extending edge bar St with Sx is equal to T merely replace the factorization by Yt is equal Zx, extending the current prefix from S to T. See the following figures here. We can find here. Example: let X capital consist of A, B, B, A, B, 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 A, B, A, B, A, B, or the alphabet A capital, which consists of two letters A and B. The non-empty prefixes, in addition to the word in X capital, are the word B, A, B, B, A, B, 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 A, B, A, B, 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 and B, A, B, A. So the graph has 11 vertices. The prefix graph G capital sub X capital is given in the following figure. We shall prove that the set X capital is a code if and only if there is no pass in the prefix graph G capital X from the vertex in X capital to a vertex in X capital. In our example, there exists a path from A to itself, from edge A to itself, or to A, B, 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 A, though the set is not a code. So we start with the Lima describing paths in the prefix graph G capital X capital. First, we need a definition. To factorization, x1 so on xn and y1 so on ym of a word are called disjoint if the word x1 so on xn is not equal y1 so on y j for I from 1 to n minus 1 and j from 1 to m minus 1. We say simply that x1 so on xn is equal y1 so on ym is a disjoint double factorization when two factorization x1 so on xn and y1 so on ym of the same word are disjoint. Lima. There exists a path of length n greater or equal 1 from S to T in the prefix graph of X capital if and only if there exists x1 so on xk, y1 so on yl in X capital such that as the word as y1 so on yl t is equal the word x1 so on xk, or the word as y1 so on yl is equal as the word x1 so on xk t are the joint factorization with k plus l is equal n, and moreover s is a prefix of the word x1, respectively a prefix of the word t if k is equal 0. The label of the path is the word y1 so on yl t in the first case and the word y1 so on yl in the second case. The first case occurs if and only if the path contains an odd number of crossing edge, and the second case occurs if and only if the path contains an even number of crossing edges. Example. Consider as an example of the path, the following path here. In the previous graph, it is represented in the following pictures. This path has length 4. The first 3 edges are crossing edges, and the last one is an extending edge. It corresponds to the joint factorization, so that factorization. Here, L is equal 1, K is equal 3, and the product of label is BA, 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 BBB. So we have that. And the The following path has two more edges. It corresponds to the disjoint factorization, which shows that the set X capital is not a code. So we repeat Lemma 2.7.2 and give a proof of this Lemma. Assume first that there exists a path of length n greater or equal 1 from S to T. If n is equal 1, then either st is equal s or sx is equal t with x from x capital. Thus, there exists a double factorization of the desired form for n equal 1. Assume now n is greater or equal 1 and that there exists edge from t to u. And by induction, the word s y1 so on ylt is equal to the word x1 so on xk, or the word sy1 so on yl is equal to the word x1 so on xkt, and either tu is equal x belongs to x capital, or tx is equal u for some word x from x capital and u does not belong to x capital. So there exist 4 cases to take. We consider first case if the word x y1 so on ylt is equal x1 so on xk and tu is equal x belongs to the set x capital, then the word s y1 so on yl x is equal x1 so on xk u. And these factorizations are again joined because the word u is a proper suffix of the word x. The second case, if the word s y1 so on ylt is equal x1 so on xk and tx is equal to u for some word x from x capital, then we get s y1 so on ylu is equal x1 so on xk x. And again, the factorizations are disjoint because the word u is a proper suffix of the word t, and so of the word xk. The third case, if the word sy1 so on yt is equal x1 so on xkt and tu is equal x which is belongs to x capital, then the word su1 so on ulu is equal to the word x1 so on skx, and the factorization are disjoint because the word u is a proper suffix of the word x. Moreover, if k is equal to 0, then the word s is a prefix of the word x, because the word s is a prefix of the word t and t is a prefix of the word x. And the fourth case, finally, if the word s u1 so on yl is equal x1 so on xk t and tx is equal to u for some word x from x capital, then we have that the word s y1 so on ylx is equal x1 so on xku. The factorization are again disjoint. If k is equal to 0, then the word s is a prefix of the word t and t is a prefix of the word u, so the word s is a prefix of the word u. Conversely, assume that there exists a double factorization that the word sy1 so on ylt is equal x1 so on xk, or a double factorization that the word sy1 yl is equal x1 xlt with k plus l is equal n. If n is equal 1, then k is equal 1, l is equal 0 in the first case, and k is equal 0, t, l is equal 1 in the second case. Indeed, the value k is equal 1, l is equal 0 in the second case is ruled out by the condition that the word s is a prefix of the word x1. Thus, there exists a crossing edge bar st in the first case and an extended edge st in the second case. Assume that n is greater 1 and the word sy1 so on ylt is equal x1 so on xk. Since the word t is not equal as the word xk, so here must be k sub. One of these words is a proper suffix of the other. Suppose first that the word t is a proper suffix of xk, and the set xk is equal the word ut. Then there exists an edge from the word u to the word t in the so edge u to edge t in the graph g capital x capital, and moreover the word s y1 so on yl is equal the word x1 so on x k minus 1 u. If k is equal 1, then the word s is a proper prefix of the word u. Otherwise, the word s remains a proper prefix of the word x1. Thus, the induction applies, and there exists a path from the edge s to the edge u of the length n minus 1, hence a path of the length n from s to t. Assume next that the word xk is a suffix of the word t and set t is equal uxk. This defines an extended edge ut. Thus, we have that the word s y1 so on ylu is equal x1 so on xk minus 1. Since the left hand side is not empty, the word s is a prefix of the word x1. The conclusion and again followed by induction. In the double factorization, if the double factorization is the word sy1 so on yl is equal x1 so on xkt, then since the word s is a proper prefix of the right hand side, one has l is greater 0. If the word yl is a proper suffix of the word t, then t is equal u then the word t is equal uyl for some word u, and there exists an extended edge ut. Replacing t by uyl gives that the word sy1 so on yl minus 1 is equal to the word x1 so on xku. Either the word s is prefix of the word x1 or k is equal 0, and then the word s is a proper prefix of the word u if l is greater 1 or s is equal u if l is equal 1. In the first case, there exists a path from edge S to GU. In the second case, there exists just the edge ST. Finally, suppose that the word T is proper suffix of the word YL. Then we have that the word YL is equal to UT, and thus there exists a crossing edge UT. Next, the word S, Y1, so on, YL minus 1, U is equal X, so on, XK, so K is greater or equal 1, and the word S from I a prefix of x1. There exists again a path from S to U of the length n minus 1 by induction. This completes the proof. We have the following theorem 2.7.4. A set X capital of non-empty words is a code if and only if there exists no path in its prefix graph from a vertex in X capital to a vertex in X capital. The proof. Assume that there exists a path from the word S from X capital to the word T from X capital in the prefix graph G capital X capital. Then there exists a joint double factorization of one on the form described in Lima 2.7.2. In both cases, this gives a double factorization of a word as a product of the word in the set X capital. Conversely, assume that the set X capital is not a code and consider a shorted word W in the semigroup generated by the set X capital that has two distinct factorization. W is equal the word W is equal x1, so on, xn is equal the word x1, so on, is equal y1, so on, ym, with xim and yj from the set X capital. We may assume that x1 is a proper prefix of y1, then there exists a path from x1 to ym of the length m plus n minus 2 in the graph G capital X capital. This completes the proof of our theorem. Given a finite graph, G capital, many properties of G capital can be checked in a linear time with respect to the size of the G capital of the graph G capital. There exists a size is a total number of vertices and edges of G capital. Among these properties, there exists the extension of cycles, the existence of paths between a distinguished set of nodes, and so on. All properties described in the previous lecture are of this kind. This required to estimate the size of the graph G capital X capital of the code or the set X capital. Proposition 2.7.5. Let X capital be a finite set of words with an element, and n capital is assumed of the length of word from the X capital, b the sum of length of the word in the X. The prefix graph G capital X capital has at most n capital vertices and at most n capital edges. Let's prove. The vertices of the graph G capital X capital are the non-empty prefixes of the word in the X capital. There are at most n capital minus 1 of them. Next, consider a vertex T and an edge ST entry T. If the edge ST is the crossing edge, then ST belongs to S capital is longer than T. And if the word t is equal sx for some word x from x capital, then x is shorter than t. So a word x in the set x capital is contributed at most one crossing edge, or it contributes at most one extended edge. So the total number of edges entering the word t is most n. And the total number of edges in the graph G capital X capital is at most n multiply n capital. This completes the proof proposition. Coloring. Coloring 2.7.6. Given a prefix graph G capital X capital of the set X capital of n words of total length n capital, it can be taken in time O and capital where the X is capital is a code. The proof. This is a direct consequence of the previous discussion. It remains to show how to construct the prefix graph G capital X capital of a finite set X capital in the linear time with respect to its size. That is, with respect to n multiply n capital, where n is the number of the word in S capital and n capital is the sum of the length of the word in X capital. The construction is in three steps. First, a simple automaton recognizes that the set X capital is constructed. This automaton is deterministic but not complete and has the shape of tree. Such an automaton is usually called a trie. The vertices of graph G capital X are among the state of this automaton. Next, the automaton is converted to what is called a pattern matching machine. This is done to equipping the trie with a faulty function. The role of this function is to provide, in the case a transition does not exist for some letter in some state, another state where one can look for a possible transition. As a result, the pattern machine matching machine recognizes, with the aid of the faulty function, the set A capital star X capital of the word extended in the word in X capital. These two preliminary steps are used. In final step, we compute efficiently the edges of the graph G capital X capital. Given a finite set X capital of the word over the alphabet A capital, the trie of the X capital is the automaton whose set of state is the set P capital of prefixes of the words in X capital. The initial case is the empty word. The end states are the words in the set X capital. The next state function is defined for P from P capital and A from alphabet A capital if and only if PA is in P capital, and then P multiply A is equal to PA. The trie of the set X capital can be constructed very simply by increasing the word of X capital onto tree that is initially reduced to the empty word. The following this described follow this algorithm to calculating the trie of X here. This algorithm clearly computes the trie in time of n capital, where the n capital is the sum of the length of the word in the set X capital. Example: the trie of the set X capital, which consists of A, B, B, A, B, 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 A, B, A, B, A, B, is given as the following figure. The trie of X, the trie of X, view with the automaton is accepted port is X, yeah? Given a finite set X capital of the word over the alphabet A capital, the following function is extended to be used when the next state function P multiply A is undefined in the trie of the set X capital. It gives a state Q where a new trial for the computation of the next state should be started. The following function f of the set X capital is defined on the set of non-empty prefixes of X capital. For P from P capital and P is not equal empty word, f of P is the longest proper suffix of the word P, which is in the set P capital. For the empty word, we put f of empty word is equal empty word. The pattern matching machine of the set X capital is the automaton derived from the trie of the set X capital by extending the next state function on the set P capital by the formula P multiply A is equal to PA if PA belongs to P capital, and otherwise F of P multiply A. Moreover, the state P is terminal if f of P is terminal. The function computer faulty of T computes the faulty function for the trie T, and is described in the following algorithm. You can say phi here. The pattern matching machine is obtained by construction first the trie and then the faulty function. Example, the pattern matching machine of the code X capital, which consists of A, B, B, A, B, 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 A, B, A, B, A, B, is given in the following figure. Yeah. Viewed as in the automaton, the chapter with the word in A capital star X, and the pattern matching machine state are in gray. The float function is presented by dotted wedges. A state P is terminal for the pattern matching machine if it is a word in the set A capital star X. It appears useful to know the longest suffix of the state P that is in the set X capital. Call this sigma of P. The function sigma is undefined on non-terminal states, and for terminal state it is given by the following formula: sigma of P is equal to f of P if f of P is the set X capital, and otherwise sigma of f of P. This shows that provided we remember those states that are in X capital is quite easy and linear with respect to the number of states to compute the function sigma. We are now ready to compute the edges of the graph G capital X capital. Each word X in the set X capital may be produced several crossing edges as T. This is a crossing edge provided a suffix T is also a prefix of the word in X capital. All these suffixes are enumerated by the faulty function. Thus, one gets the following function for computing the crossing edges. Give the following algorithm, yeah. The only Tricked line is a computation of the vertex corresponding to the word x t minus 1. This may be done by maintaining for each x each word x in the set x capital in array of pointers to the vertices of its prefixes indexes by their length. So from the length of the word x and the length of the word t1 obtains the length of the word s, thus s is constant type. The computation of extended edges is quite similar. Given a suffix t, we'll look for all suffix x of t. Each of these suffixes gives an extended edge st with st is equal t. To loop through the suffixes of the word t which are in the set x capital 1, iterates the function sigma. Thus, the function is described by the following algorithm. Again, the tricky point is the computation of s is equal to tx minus 1. To do this, one maintains for each vertex p a pointer to the longest word in x capital, for which word p is a prefix. In the present case, the word s is a prefix of the word t, so they share the same longest word in the set x capital, and the trick of the array used previously applied again to give the vertex of the word s in constant time. Altogether, the following function computes the prefix graph of the set x. This algorithm describes this. We can finally state the following result as a consequence of the preceding construction. Proposition 2.7.9. Given a set x of n words over some alphabet a capital of total length n capital with assume length of the word x from x capital, the prefix graph G capital X capital B can be constructed in the time and space O of n capital. So we finish our lecture. I wish good luck, good health, and goodbye.